Welcome to the Data Science Institute's virtual seminar series. My name is Dr. Sarah Mackey from Lawrence Livermore National Laboratory. Here at Lawrence Livermore, data science has become an essential discipline in many of our key program areas. LLNL is home to many challenging datasets, as well as home to some of the world's most advanced supercomputers. Our data science staff work in a variety of areas, including machine learning, artificial intelligence, big data analytics, statistical inference, predictive modeling, and uncertainty quantification. The Data Science Institute acts as a central hub for our lab's data science activities. We host events like this seminar series in order to introduce new ideas and potential collaborations to our laboratory staff. We invite speakers from outside the laboratory, from the Bay Area and beyond, to share their innovative approaches with our data science community. We're pleased now to include a wider audience in our seminar series through these recordings. You can read about past speakers at our website at data-science.llnl.gov, or you can email us at datascience@llnl.gov. Thank you and enjoy the seminar series. Sarah Friedovich-Kiel is a postdoc scholar at Stanford University, where she works on foundations and applications of machine learning and signal processing in computational imaging. She is currently supported by an NSF Mathematical Sciences postdoctoral research fellowship. She received her PhD in electrical engineering and computer sciences in 2023, just recently, from UC Berkeley. And she has a bachelor's in electrical engineering from Princeton University that she received in 2018. During her time at UC Berkeley, Sarah worked as a student researcher at Google Brain and collaborated with researchers here at LLNL, as well as at University of Southern California and UC San Diego. So with all that out of the way, I'll turn the time over to Sarah. Thank you, Sarah.
Cool. Thank you. Thank you all for being here. Just to reiterate, feel free to interrupt me at any time with a question, both the people here and if you're on WebEx. I can't really see you, so if you have a question, just say it, I think. Okay.
Yeah, Holly is online, and if people have questions online, Holly, you can feel free to...
Okay, sounds good. Okay, so just to start, I want to define the class of inverse problems, which is where all of my work that I'll talk about fits under. So in an inverse problem, we have some structure in the world that we want to model. So as an example, here's Saturn. We have the ability to take measurements about this object. So for example, like satellite images. And we have some forward physics model that describes how those measurements were taken. So if I knew the world, I could simulate the construction of my measurements. The goal in an inverse problem is to invert that forward physics model. So just given our measurements and the physics model, we want to recover what happened in the world. So inverse problems are a very broad class of problems. So they include basically any kind of medical imaging you can think of. I give some examples here like CT and MRI and ultrasound. Also other sensing modalities like sonar or radar or LiDAR. And then also at the microscopic scale, things like cryo-electron microscopy or any other sort of computational microscopy methods. Computational telescopy, there's all sorts of things I'm not listing here. Okay, so the inverse problem that I'm going to focus on for purposes of this talk comes from computer vision and graphics. So the structure we want to model is just any object in the world that you can see with your eyes. The physics model is just a camera, so we're going to take color photographs. So the measurement here is a bunch of photographs from different viewpoints, different angles. And then from these multiple photographs, I want to reconstruct a photorealistic 3D model of the object that I could then render from whatever viewpoint I care about. Okay, I'm going to spend one slide talking about prior work just for some context, but feel free to ask questions or, yeah, okay. So the main prior work I'm going to talk about, the only one I'm going to talk about, is neural radiance fields. There are lots of others, obviously, but this is the most relevant for right now. So it's called NeRF for neural radiance fields, and this is how it works. So can I walk away from the microphone? Okay, or actually, theoretically I have a pointer. It's okay, I'll just point. So, okay, So given my training views from different angles, every pixel in every training view corresponds to a ray through the scene. And so during training, NERF will cast these virtual rays out from every training pixel. They'll take a bunch of samples along each ray, so this is this black dots. And then their core sort of scene is this F theta here. It's an MLP, so multilayer perceptron, that's representing the scene. And that model takes in coordinates of a point and outputs how dense is it here, like how much does this place absorb light, and what color is here. So that's RGB color and sigma is density. Okay, so by casting all these rays through the scene, now at every point they're asking their MLP what's here, and then following this volume rendering formula, which is here, to compute the final ray color. So this is accumulating all of these samples, like all the colors from all the sample points to get a final pixel color, and then they'll compare that pixel color to the ground truth, and the whole thing is differentiable through this rendering formula. So at the end of the day, they can update their parameters in their F theta. Okay, so NERF made a huge splash in this computer vision community because it produced really nice reconstructions. But it had sort of two limitations that, well, more than two, but two that I'm going to talk about. Which were, so one is it took more than a day to train fully on a single scene. So it was very slow. And then secondly, there was this sort of lack of understanding that the entire scene was represented as a black box that you just like ask this neural net what's here and it tells you. But we didn't really understand like why it worked. Okay, so I'm going to talk about 3 projects today. Hopefully I have time, that try to address these 2 sort of questions about NERF. So the first one is removing the neural net. Actually, the first one's going to address both of those limitations, and then the second one will address the limitations of the first. Okay, I'm rambling. Let's start. So I'm going to start with planoxels, which is sort of a follow-up to NERF where we get rid of the neural network, we make things more explicit and also a lot faster. And this is joint work with some awesome people down here. Okay, so this is how planoxel works. So this is all of our training views that we see outside. So all of our training cameras, we cast those rays through the scene. And now we represent the scene as a voxel grid. So all of these little dots are the parameters in our model. And now when we take samples along a ray, instead of asking a neural net what's here, we're going to just interpolate the values of the neighboring voxels. And then we'll follow the exact same formula to combine those samples along the ray into a final pixel color. We'll do the same like mini batch optimization with just sampling rays and updating our parameters. But now the parameters that we're updating are these voxel values in our grid, as opposed to the parameters of a large MLP. Okay. So on the bottom right here is training time. This is like wall clock time. And NERF is on the left and planoxel is on the right. And this is seconds. So planoxel is going to train to completion in around 10 minutes. And NERF, as I said, it takes about a day. So part of this speed up is due to, it's a lot faster to just do some grid lookups than it is to evaluate an MLP. That makes sense? Yeah. Multilayer perceptron? Yeah. Yeah, so there was actually a prior work, I'm blanking what it's called. But there was a prior work that did basically a voxel grid and then a CNN next to it. Neural volumes. Yeah. So check out neural volumes. Neural volumes actually came out maybe slightly before NERF. So NERF was building on neural volumes. But yeah, that has also been done. Okay. So it's now grayed out a little bit, but in the top here you can see the final like training time, days versus minutes, and then this dB number is PSNR, which is peak signal to noise ratio. It's a log scale for quality, so higher is better. So just to show, it's slightly covered up, but we're matching or exceeding the quality of NeRF under this metric, but getting there a lot faster. Okay, just to show some more fun videos comparing quality on different scenes. This is after optimization's done. I hope it's sort of visible, but Planoxyl is getting much sort of greater detail. And the reason for this partly is that we do have a much higher memory model, so we have it's a sparse voxel grid, but the resolution goes up to 512 cubed. And these images are only 800 by 800, so we can actually represent pretty much everything. So one, I'll talk while this plays. So one sort of limitation you might expect from a voxel grid would be that it has to be bounded. So one of the things we wanted to show in this project was that that's not true. You can represent an unbounded scene even with a voxel grid. So in this case, for forward-facing scenes, we do it with a pretty standard scene warping called NDC, normalized device coordinates. Basically, it warps the space so that voxels in the front are sort of smaller and high resolution, and voxels as you get further away become larger. So this allows me to represent a scene as unbounded in depth, but have high resolution in the foreground. And then we can do something pretty similar to represent full like 360 unbounded scenes. So there are multiple ways of doing this. The way we did this in Planoxyls is with a dedicated background model. So here we have a voxel grid that represents the foreground, and then we have sort of concentric layers of, it's called a multi-sphere image. So it's like sort of spherical images receding outwards like an onion from our central like foreground grid. And all of these are connected to each other with interpolation. So if I want to sample a point between two layers, I'll interpolate the values stored at the different nearby layers. And so this lets me do things like, in the video you'll see we segment out foreground versus background, but we optimize them together. And this is on real data now. Actually, all of these 360 scenes are real data. Okay, so one of the sort of main points we wanted to make in this Planoxyl paper is that in NeRF, there were sort of multiple things that NeRF did that was different than prior work, and there was this question of like, which piece of NeRF is the secret sauce? Which part really makes it tick? And so part of what we're showing with Planoxyls is that it's not the neural network. You can do everything here without any neural networks, and instead we sort of posit that the secret sauce of NeRF was this differentiable volume rendering formula. So that formula I showed at the beginning, I'll show it again later. It's not new to NeRF. It actually came from a paper in 1995, but it was first used by NeRF in this optimization setup to learn a scene. And so that sort of differentiable formula really makes a difference. I also want to explain a little bit about what are the sort of key components that we used in Planoxyl that made it work, because it also took multiple attempts to get Planoxyl to work. So probably the biggest thing that made it go from not really working to working was trilinear interpolation. So usually when you think of a voxel grid or any sort of grid, you imagine that like color would be constant throughout the voxel, and you'd get these little cubes. That's what like nearest neighbor interpolation does. It says if I want to sample a point, find me the nearest voxel and take that color. Instead, we do trilinear interpolation, which is like one step more complicated. It says, okay, find me all of my neighbors and do some linear combination of those neighbors weighted by how close I am to each neighbor. And trilinear interpolation, it has sort of two benefits. So one is you get effectively subvoxel resolution because color can change within a voxel. And also it makes the optimization work a lot better because now there's not these sort of discrete cutoffs that if I sample a little bit to one side or the other, I'll get a completely different answer. Now it's a continuous function, and that's really nice for getting gradients that we need to optimize. So this is an example of the same resolution grid optimized with nearest neighbor interpolation versus trilinear. And you can tell it's just a lot better with trilinear. The other thing we do is explicit regularization. So in NERF, there's no explicit regularization. All regularization is implicit just from the neural net structure. In Planoxel, it's a grid. It can represent anything. So we have to explicitly regularize to sort of push our model towards solutions we like. So in this case, we use a very simple regularizer called total variation, which basically says I'm going to penalize my model for having lots of edges. I want to have few edges. And this is good for most objects have sort of coherent edges. So it encourages things to be sort of blobby and objects. And you can tell this is a zoom in on one of those forward-facing scenes with the fern. If we don't regularize, we get all sorts of floating junk in the air. And if we do regularize, we get very clean ferns. So just to sort of lay bare, you don't need, I think one of the arguments people make about neural networks is that they have some implicit regularization, and that's true. But explicit regularization also still works. Okay, so the last thing I want to say about Planoxels that I think it offers compared to NERF is recognizable artifacts. So let me explain what I mean by this. Okay, so this is another forward-facing scene where this model was trained on a set of views that are nearby, and this is a test view that we're showing that's towards the edge of that range of angles that was trained on. And so this bottom left region that's circled was sort of under-supervised during training. So the model is kind of making its best guess for what's there, and you can tell NERF sort of guesses some stuff, and Planoxel just sort of fades to gray. The reason Planoxel is just fading to gray is we initialize it to be cloudy gray. And so if it's under supervised, it's going to be gray. And this sort of blurring is coming from the regularizer. So we're encouraging it to not be all edgy, just be smooth. Whereas NERF is trying to sort of make up something to go here. So this doesn't matter so much for computer vision. In computer vision, it's pretty easy to collect lots of data, so it's not a huge deal. But for other types of imaging, like those other inverse problems I mentioned at the beginning, it might be harder to collect data, and we might be relying more on our priors, and we might be in a situation where there's a greater cost to having a wrong reconstruction. For example, in medical imaging, you don't want the reconstruction to be making things up. So as sort of a first step in that direction, it's helpful if your model at least produces sort of obvious artifacts when it doesn't have enough data. So you want to at least recognize when you shouldn't trust your model. So there's a lot more work to be done here, and that's something I'm interested in doing in my postdoc, but at least for now, this is sort of a step in that direction. Okay, so I've been saying lots of good things about Planoxels. I want to switch gears a little bit and talk about the limitations of Planoxels. So there's sort of three assumptions we make in Planoxels that I want to address. So the first is we assume that all of my training photos have perfectly consistent illumination. So you may have seen on some of those last 360-degree scenes where they were outdoor that it wasn't quite perfect. Part of that was because in an outdoor scene, the light is very bright, and when you take camera photos from different directions, the exposure changes on the camera. So you sort of violate this consistent illumination assumption. The second assumption is no moving objects. We need everything to be perfectly still while we collect all our data. And then the last piece is high model memory. So we do use a sparse voxel grid, but it's still a voxel grid. Each Planoxel model is around 2 gigabytes of memory. So it fits in a GPU, it works, but it's not great if you want to represent like many scenes. So this sort of motivates the second part of the talk called K-planes. You can think of it as Planoxel 2.0, where we're going to address these limitations. Actually, all of them. So just to motivate the K-planes construction, so in this plot on the right, on the x-axis is the dimension of the space we're trying to represent. So a 3D, like 3 here means like a 3D volume, like we do in Planoxels. 4D would mean a dynamic volume, so like x, y, z, t. And I can give some examples of at least 5D. You could have something where maybe you want to do hyperspectral imaging, and so you also care about wavelength in addition to x, y, z, and time. Or in a protein modeling setup, maybe you believe that your protein can change shape, but only along like 2 or 3 dimensions of variability. So there are reasons to care about higher dimensions, but here we'll only show 3 and 4. And then the y-axis here is the number of parameters in the model, and this is a log scale. So the planoxyl, like if I just had a dense grid, this is going to grow. It'll look linear here. It's actually exponential. So if I want to go, if I need 2 gigabytes to represent a static scene, I'm just going to give up going to 4D. That's just not going to work if I want to have reasonable resolution. But K-planes grows much more slowly. So we're actually going to be able to represent these higher dimensional scenes with K-planes. Yeah. By texture, do you mean like local like smoothness kind of, or like colors? Yeah, so some of the color bit is coming from, I think it's part of it's coming from that inconsistent illumination, that if I'm trying to optimize a single color model that's supposed to represent, so I didn't have a slide on this, but in Planoxyl we represent color with spherical harmonics, which are just a basis for functions over spheres. So it's a function over a sphere because I expect that the color of an object might be different depending on where I look at it from. So if I have a shiny object, I want it to be like shiny from this angle, but less shiny from that angle. But we optimize a single set of spherical harmonic coefficients for all the training views. So we expect that it's at least consistent among different views. If I have like a real world scene where the exposure changed, then it'll sort of confuse the optimizer. It'll get different information from different viewpoints. And it may, like, depending on the order that rays were seen during optimization, it might land somewhere at this point, but somewhere else at the point next to it. And so you can end up getting these sort of not quite smooth textures. Decently, but not perfectly. Trying to think if I have a good example of this. Oh, actually, there are some examples in here. So like the water in here is an example of a specular surface. And when it finishes this one, there's a materials scene. Yeah, this one, so like that chrome ball is very specular. And also this drum set is pretty specular. You can kind of tell, like, actually on the drum heads, there's some of that like not quite smooth texture. Yeah, I think part of this, I guess so for here, the explanation is not differences in training, like training exposure, because these are synthetic scenes where it is really consistent during training. Here, I think the reasoning is that, so spherical harmonics, it's a basis. If you want to represent really specular things, you would need a lot of basis functions to get a lot of detail. And we cut it off at degree 2. So we represent sort of blobby specularities, but we don't represent like really sharp specularities. And so for something that's really smooth like this, it's gonna not be quite right. Yeah, and that's like, it's a trade-off of memory, where if I want to represent more specular objects, I'm gonna need to represent more spherical harmonic coefficients, and it'll make my 2 gigabytes into 5 gigabytes or whatever. It's a good question. I have to click back to where I was. Okay. Any other questions while we're in between parts? Okay. So the next project I'll talk about, you can think of it like Planoxyl 2.0. This is, it's called K-planes, and it was collaboration with a slightly different set of great people. Okay, so here's the idea. So if I want to represent a 3-dimensional space, instead of doing it directly with a voxel grid, I'm going to do it with a set of 3 2D planes representing xy, xz, and yz. And it's 3 plane. Well, I'll get there actually. Okay, if I want to represent a 4-dimensional space, this is my attempt at representing a 4-dimensional space. I'm going to use 6 planes. So now my variables are x, y, z, t. So I'm going to need 6 planes. I'll have the same 3 planes I had before for x, z, y, z, x, z. And then I'll need 3 more planes for x, t, y, t, and z, t. And so the general pattern here, we call it k-planes because if I want to represent a scene in d dimensions, I need d choose 2 planes, which will be every sort of pairing of coordinates. So it's just a nice heuristic for representing scenes as planes. The reason we want to use planes, so we like grids because they're easy to sample into, they're very interpretable, you can sort of localize all of your parameters in space. We like 2D grids as opposed to 3D because 3D grids are expensive. It's hard to store them at high resolution, it just takes a lot of memory. And 1D, so we don't really want to go 3D, we want to go less than 3D. And we don't really want to do 1D because that's just not very expressive. So 2D was sort of this happy medium where we have enough memory, we can represent sort of, a plane is basically an image. So our model is like the same amount of memory as a stack of images. And so you can represent that in memory pretty easily. And this is just a way of sort of constructing an arbitrary dimensional space out of planes. Okay, so I'll show how this works. So now we have potentially a video camera. We're still going to shoot rays through a scene, and we'll take samples along the ray. I'm just showing one sample because it'll get complicated. Okay, so now I have my 3, let's imagine this is a static scene for now. I have my 3 planes, x, z, y, z, and x, z. That x, y, x, whatever, you know what I mean. Okay, so I'm going to project my point into each of these 3 planes, and I'll do now, instead of trilinear interpolation, I'm going to do bilinear interpolation into each of my planes. So I'm going to look up the 4 sort of neighboring points in the grid, and I'll interpolate them. And then I'll take these 3 features from my 3 planes, and I'll multiply them together into a feature for this point. And I'm actually going to do this at multiple scales. So I'll represent the same, it's sort of cheap to represent things at lower scales, and this is a common thing in graphics. So I'll do it. I'll represent my scene with each plane at multiple resolutions. Okay, so I'll just do the same bilinear interpolation at each scale, and I'll concatenate the scales together into a feature vector. And if it's a dynamic scene, then I'm going to do the same thing in my xt, yt, zt. So now my point has a 4-dimensional coordinate, x, y, z, t, and I'll project it into each of my 6 planes, do this whole interpolate, multiply, concatenate, and now I have the feature vector. And I can interpret this as my 3 planes that don't involve t as like the static component of the model, and then the 3 planes that do involve t we'll think of as the dynamic component of the model. Okay, and by combining these, I have some feature vector that I'm calling f of x, y, z, t. Okay, so now we want to decode this feature vector into a density and a color. Okay, so part of the shtick for planoxels is no neural nets. So we're going to actually show 2 different decoders for k-planes, one that uses neural nets and one that is explicit. Okay, I'll start with the hybrid one. So this is very similar to a construction from IncidentGP, which is another similar paper, where we have two MLPs. They're very small compared to the NeRF MLP. So these are like 2-layer itty-bitty MLPs that one of them takes the features and predicts sigma, which is density, and some more features. And then the other takes in those features, and D here is viewing direction. So we want the color to be view dependent and the density to not be view dependent. So that's how we achieve this. Density is predicted directly from features, whereas color takes in features and view direction. Okay, the explicit decoder is a little bit different. It's based on just dot products. So we kind of took inspiration from spherical harmonics. In spherical harmonics, you can evaluate this set of basis functions into like a vector, and then you dot product it with your coefficients that you've optimized, and that's how you decode. So here, instead of using spherical harmonics, we're going to use some learned basis, where v sigma, that purple vector, is literally a vector that we optimize the numbers in the vector, and that's our basis for density. So we just dot product it with our features and get density. And then for color, we have a little MLP that just takes view direction and outputs a vector. And this is our sort of learnable spherical harmonics, if you will. So instead of being a hard-coded set of basis functions, it's a learned function that still outputs some basis vectors. And we dot product that basis vector with our features and we get color. Yeah. Yeah, so depends on the data set. We usually use either 16 or 32 per scale, and then we might have like 3 scales. Yeah, there's a trade-off there also where the more features you use, the more memory and time it takes, but also the higher quality you'll get for specularities. Okay, so back to videos. So now this is a reconstructed scene where I can move the camera while time is progressing. So the guy can cook and we can move the camera. And this happened to be with the explicit decoder, but I can show side by side the same scene with either decoder, and we get very similar results. So part of the point of having these 2 decoders was just to show that you still don't really need the MLP. You can still do things explicitly, and you don't really lose much. Okay, we can also use, oh, yeah. Yeah, the colors, it is possible that they optimize like slightly different color bases, but the sort of overall like numerical quality is about the same. Yeah. I think you said, I can like partially hear you. I think you said that it should do better with low light. Why would that be?
That might be the screen on this side of the room. The left image is more vibrant.
Oh, that could do it. It's not a perfect diffuser. Okay. Interesting. So because we have this like planar representation with the space planes and the time planes, we can use this to actually decompose space and time in the reconstructed video. So I'll show that a little bit. So this is the same video. If I render it with only the static planes, so I remember the features are multiplied between the planes. So if I set the time plane features all to 1, then I'm basically only using the static planes. And I get this sort of averaged out like static image with a piece of the guy's head to the side for some reason. And then on the right, if I just subtract like the full reconstruction from the static part, I can pretty clearly see the motion. And this is just to sort of inspect. If I look at the XT plane, this is just like averaging over the features, then so gray, like the plane gray is 1. So this is saying there's no motion in this part of the scene. And then you can actually see like the left and right hands of the cook. You can tell he's like moving his right hand more than his left hand during the video. Yeah. Yeah. Yeah, so I'll show some examples of both actually. So for this data set, this data set's called Diner, if you're curious. It was collected not by me, but with a like very nice camera rig that has around 20 video cameras that are just like arranged in a grid and they're all synchronized. So you have like multiple viewpoints at each time step. There's another data set, this one, which has multiple synthetic scenes. So that one was a real data set. This is a synthetic one, where for this synthetic data set, it's monocularized in the sense that at every time step, I just get to see one view, but it's from a random position. So the camera is sort of zipping and zooming around the scene. So I get sort of multi-view, but not at the same time step. And for K-planes, we don't really care. We can optimize with, as long as you give me points that I know the X, Y, Z, T, I can use them to optimize. But the quality will, of course, vary depending on how good the data was. Okay, so I want to spend a brief moment on regularizers. So on the left here is a reconstructed video. We use actually 3 regularizers, but I'm going to illustrate 2 of them. So the same total variation in the middle, which is saying, give me sparse edges, give me like coherent objects in space. We do this over the spatial dimensions of our planes. So in the space planes, we do 2D total variation. In the time planes, we do 1D total variation over the space dimension of the plane. And then over the time dimensions, we penalize for acceleration. So this is basically saying, give me like smooth motion over time. And then the third regularizer that I didn't show is we actually penalize motion in general. So we say, if this part of the scene does not move, then put it in the static planes. And so that's how we get things like the XT plane where it's all 1 except where there's motion. So we regularize it towards 1. Okay, the last piece I'll say about K-planes is that because we have this sort of more flexible decoder where we learn a basis for color, we can actually adapt now to changing lighting on the same scene. So these are examples of scenes reconstructed from tourist photographs. So these are like known sort of landmarks where lots of people take photos at different times of day and times of year. And we can sort of add an extra parameter to our color decoder that tells it or lets it decide, like, is this, what time of day is this? What time of year is this? And then it can choose a different color basis for different images, but it'll learn consistent geometry across all the images. So I'm now like moving the camera while interpolating between like day and night, for example. Okay. So actually the last thing I want to say about K-planes, I wanted to show a few examples of how to use it. So it's been integrated into, so all the code is out for all of these, but K-planes is particularly sort of friendly to use because it's been integrated into some nice toolboxes. So one is NeRF Studio, which gives you some nice visualization tools, and it makes it easier to plug in your own data sets. And then NeRF ACK is for NeRF acceleration, and this is, so we already have some sort of tricks in K-planes that sample more efficiently and speed up training, but this actually speeds it up even more with a different fancy sampling strategy. And then there's also some concurrent work with K-planes that uses a very similar model. So there's one called HexPlane that focuses on dynamic scenes and came out like literally a day apart from K-planes from University of Michigan. And then there's also from Meta AI a generative project called Make a Video, where they train a generative model that you put in some text prompt and it'll generate planes that will then render into a video. So for example, this is one from their website, like dog superhero, and it generates this using like a 6-plane representation. Okay. Let me take another brief pause. The last part of the talk it'll be short and it'll be a dive into theory. So we're done with pretty videos. Okay. And this last part is ongoing. So I have some sort of partial results that I'll show, but it's not quite all there. Okay, so I want to return to the measurement model that I showed at the very beginning with NeRF. This is exactly the same measurement model that NeRF uses, and let's try to get a better understanding of it. The goal in this part of the talk and this project is I want to argue or reason about when is it possible to get a correct reconstruction. So given this forward model, things like how many images do I need to get a 3D reconstruction? And what kind of quality can I, like if you tell me how many images you collected, I should be able to tell you what error you should expect on your reconstruction. So, okay, let's walk through this. So C hat is the color of array R. This thing in blue, sigma, is the optical density. I've been using that throughout, but sigma sub like I or J is the density of like the I sample point along array. And CI is the color of that sample point. delta J is not super important. It's the sampling distance. So we're basically approximating an integral along the ray, but we have discrete samples. So we have to keep track of how far apart our samples were. And this will allow us to do things like adaptive sampling, where maybe we want to sample more densely near an object. We just have to keep track of those sampling distances. Okay, and this first term with the exponential is transmission. So this is saying how much light made it sort of through the ray to reach sample I. And then the second part, the 1 minus exponential, is absorption. It's saying of the amount of light that reached me at sample I, how much did I absorb at sample I? Okay. So this is kind of complicated, so we're going to start with a warm-up where we're going to pretend that there's no color. Color is constant everywhere, and all we have is density. And this is actually a meaningful model because it corresponds to things like computed tomography, where there's no color, we have a single wavelength, and we care about the density of it everywhere. Okay. So let's just expand the outer sum. So the first term I have just sigma 0 delta 0, and then I'll have sigma 0 delta 0, sigma 1 delta 1, and so on. So I'm just writing out the sum. And if we sort of look at neighboring terms, we can do some canceling. So there's a minus exp of minus sigma 0, and then there's a plus exp of minus sigma 0. So those cancel. And I can also cancel the sigma 0, sigma 1 term. And so on. So the whole thing telescopes. It's great. So I can write the whole thing as just a single, like 1 minus exp of everything along the entire ray. Okay. So before I do that, so this is all well and good, but it's still like a nonlinear forward model, which is a little bit annoying because there's all of this theory out there in compressed sensing that works for linear forward models. But and the reason I say this is nonlinear is because C hat is what I measured. I measured the color, and I want to reconstruct these sigmas. And so there's this nonlinear relationship between what I measured and what I'm trying to reconstruct. But if I do this little like invert the exponential trick, I can pretend that instead of measuring C hat, what if I just measured, minus log of 1 minus C hat? I can do that. If I measure C hat, I can compute this. And now I have a linear forward model, that it's just an integral along the ray of all my sigmas. So this is great. This is actually the radon transform, which is sort of the core forward model in computed tomography, or any kind of tomography. So this is great. We have a lot of theory that tells us that reconstruction works in this setting, and it tells us how many samples we need to get what quality. Okay, so basically the problem is easy if there's no color. So let's go back. Now we have color. Okay, I'm going to try the same trick of just like write out the sum and see what happens. The only problem is it doesn't telescope anymore. The problem is I have these color terms that, like, if all the colors were equal, then they would disappear. But if they're not equal, they don't disappear. That's kind of annoying. But okay, let's work with it. I'll write it out. This is now just the full sum, where I've written it in terms of these like differences of adjacent colors. And just trust me that this I can write in matrix form. So here, now C and sigma are like the entire volume, like the color over the entire volume and the density over the entire volume. M here is like a sampling matrix. It's telling me which parts of the volume actually were touched by this ray. And then S is this cumulative sum that's implementing this, like the sigmas, the sums. And this delta, I called it delta because it's a discrete difference matrix. It's basically implementing those differences of colors. So hopefully you can kind of squint and believe that this is true. Okay, so I've made no approximations. I can write C hat as this. Now I'm going to make some approximations and say, well, okay, this is hard to work with. Let's just put some matrices B and A here, where I'll assume these are Gaussian. So the randomness here is coming from the ray sampling location. So I'm going to sample random rays and optimize my model, and I want to know like how many rays do I need to get a good model. And there's some sort of theoretic reasoning why Gaussian is a good model here for plugging in these matrices. I think for the sake of time, if you want to ask me about that, feel free, but I'm going to go on for now. Okay, so this is still nonlinear. It still has the exponential, but like maybe how hard is it? Like maybe we can still work with it. And so the theorem that I won't give the proof for, but I'll explain the proof sketch, is that if I get to take as many measurements as I want of this sort of random rays, like as many random rays as I want, but I have to follow this nonlinear forward model, then I can get perfect reconstruction in one step of gradient descent. Okay, so what do I mean by this? So my loss function here is, so by unlimited random measurements, I mean I'm truly computing an expectation over possible rays. So I get to see every ray. Pixel-wise square loss is just this L2 norm loss of my predicted color C hat compared to the true measured color C of these different rays. And this is saying that if I initialize color and density to just be 0 vectors everywhere, like the entire volume is empty and black, if I take a single gradient step in color and then a single gradient step in density, I will get exactly, with very carefully chosen step sizes, I will get exactly to the right answers. Okay, and the sort of really interesting part here would be, well, how many samples do you actually need to get a good reconstruction, if not a perfect reconstruction? And that I'm still working on, so that's not here yet. But I at least believe that it will work. Okay. So with that, I'm gonna wrap up. These are, so there's no code for the theory project. There's only code and websites for the coding project. So if you want to play with any of these models, you can go to the websites and the code is up there. But I will stop here and we can do questions.
Are there any questions in the room or online, Holly? If you can monitor that.
There's no questions in the chat. However, if anyone does want to come off mute, you're welcome to ask your question.
Can you speak to the name phenoxyls?
Yes, I should have said this actually when I introduced it. So, okay, so a pixel is a picture element. A voxel is a volume element. A plenoxel is a plenoptic volume element. The reason is, so in graphics, there's the thing called the plenoptic function, which is, it's an old idea. I'm no credit to me, but the plenoptic function represents all of the light at every direction and every position in a volume. And so this is what we're trying to represent. Instead of representing a volume, we're representing the plenoptic function in a volume. So we know at every point, where's all the light going? Yeah. Go for it. Okay, so this is in Keynote. But some of the animations are in Keynote and some of them are not in Keynote, and I just put in videos. Yeah. Yeah, the planoxyl animation. So credit to that goes to my co-author Matt Tancic, who is a wizard with Blender. So Blender is this like graphics toolbox that animators use. So it's the same tool that you would use, yeah, to animate things. Yeah.
Can you describe the data collection setup? Like envisioning lots of cameras that are all.
Yeah. Yeah. So there's, okay, so in here there's a mixture of different types of data sets. So some of them are synthetic, which is generated in Blender. It's easy, you can put a camera anywhere. The real data is more complicated. And I didn't collect any of this data myself. These are public data sets. But there's multiple options. So one is for a forward-facing scene, you can do things like build a camera rig where you carefully calibrate, like there's a literal like rig and cameras are attached to it, and you know exactly where each one is attached. And maybe you calibrate against some targets, so you really know like exactly the position and orientation of each camera. And then you also have to like calibrate it so the timing, like the frames exactly line up. So that's like, for example, the cooking video was done like that. If you have like a 360 scene with moving camera, there are different ways to do it. So one is you can have these motion capture rooms. So like the best quality data sets come from motion capture rooms where they have, it's like a room with a giant green screen around, like all around, and lights on top and cameras. And they've calibrated the entire room to have every camera, they know where it is, and then you can go in and do whatever you want and have calibrated data. There are more like casual capture kind of setups. So for example, like one of the last Cape Plains slide I showed was those like tourist destinations like the Brandenburg Gate. Those, there's no calibration. This is the easiest to work with, but the sort of lowest quality. For that, you don't have any calibration information about the cameras. You just have a bunch of like unposed photographs. And the way you get camera poses is using Colmap, which is a structure for motion library that takes these like different photos and tries to match them up and back out what the camera positions were. And Colmap actually will give you a 3D reconstruction, but it's not a dense reconstruction. It'll give you like some point correspondences. And so there are like some other methods in the same space that will warm start using like the Colmap partial reconstruction. Or even there are some that will start with the camera positions from Colmap and then even allow the camera to optimize if it wasn't exactly calibrated. So we didn't do that just to focus on the reconstruction, but in the Nerf Studio implementation for Cape Plains, they do allow camera optimization. So it's not that hard to use. That was a long answer.
It's very exciting. I mean, so much of what we do here is kind of often not using RGB cameras.
Right.
And, obscure thermal cameras, hyperspectral cameras.
Yeah.
But you can see how it's interesting to see this because, like, well, I could take the theory and here and apply it.
Yeah, exactly. I mean, the same, so like this volume rendering formula is true for light. It doesn't care what wavelength it is, with some exceptions. Like it doesn't handle scattering and so on, but it's decent. So you can use the same thing for like X-ray or I haven't tried using it for thermal imaging. There might be issues of like resolution, just that thermal stuff blurs. But it might work fine. I'm not sure.
Well, yeah, you might have run into problems where thermal cameras are, the quality ones are pretty expensive.
Yeah.
So you might need to go for some way of like building one camera and just moving it around in a bunch of different positions.
Yeah, if the scene is not moving, that should be fine. There might be some work of calibrating, like if you have to know exactly where each camera was, or give it some rough initialization and then allow it to optimize a little. There's also so not my work, but there's another paper called Nerfies, and there's some follow-ups of that where they do, it's like casual captures where you have a person who's maybe moving and they're also moving their phone around in front of them at the same time. And so the camera moves while the person moves. And in general, as long as the camera moves faster than the object you're trying to reconstruct, it kind of works. There are like the same calibration issues that you have to optimize over, but yeah, you can do it with moving a single camera around.
All right, well, let's thank Sarah again, and she'll stick around for a couple of minutes after the talk here in this room if anybody wants to ask a question. Yeah, thank you, Sarah, for a wonderful talk.
Sure. Thanks for having me.